Hello, and in the final one of these videos I want to introduce a slight complication to this method of determining step responses and show you what you can do about it. This is the slight problem. Supposing you have a network which has two capacitors in series wired up like this. Now, we've got a problem. While it's possible to build this network in the lab, it's not possible to analyze it using the techniques that we've used so far. And the problem is that, as we've noted, you cannot suddenly change the voltage across a capacitor. If there was 0 volts across the capacitor just before the step arrived, there must be 0 volts across the capacitor just after the step arrived. But that means that there will be 0 volts across this capacitor and 0 volts across this capacitor just after the step arrived. But that means that the voltage at this point A has a contradiction. The step is causing the voltage at A to be 1, but these two capacitors have no voltage drop across them, which means the voltage at A must be 0. If we build this circuit in the simulator and go and do a transient response and see what happens, the transient response will immediately give you an error. Cannot find a sensible solution. And that is because of this very problem. There is a contradiction just after the DC voltage is put at that point, and it won't be able to solve it. However, we can analyze this circuit using the alternative method of working out an initial value, a final value, and a time constant. And the analysis would go like this. It's a circuit. If we let the resistors be R and the capacitors be C, just have the same value for now, then we could write the frequency response as a potential divider. That would be just 1 over j omega c. That's the impedance of this capacitor, divided by 1 over j omega c plus the parallel combination of this capacitor and this resistor. Well, that would be R over j omega c over R plus 1 over j omega c. Multiply up by j omega c here, and we'd have 1 over j omega c over 1 over j omega c plus R over 1 plus j omega c R. Then multiply every term by both j omega c and 1 plus j omega c R, and we'd get 1 plus j omega c R on the top, 1 plus j omega c R here, and R j omega c here. So that's just equal to 1 plus j omega c R over 1 plus 2 j omega CR. Well, we could then work out the initial value. The initial value is the value of the frequency response when omega is infinite. And when omega is infinite, this is going to have a value of just a half, because the ones become negligible. Everything else cancels out. Our initial value is a half. Our final value is the value of the frequency response when omega equals 0. That's just equal to 1. And our time constant, that's just minus 1 over the pole in radians per second. This pole is at minus 1 over 2 CR, so our time constant is going to be 2 CR. And therefore we could write the step response as the final value, 1, minus the final value minus the initial value, a half in this case, times e to the power of minus t over the time constant, 2CR. And that would be our step response. And that method works perfectly well. And yet, as we've seen, the step response can't really exist for this circuit because there's a contradiction immediately after the step has arrived. What's going on? Well, the simulator is right. There is a contradiction immediately after the step has arrived, but that contradiction only lasts for an infinitesimally small amount of time. What would actually happen if you built the circuit in real life is that current would start flowing, both the capacitors would start charging up, but both capacitors would charge up by the same amount, because the same current would be flowing through them. And if both capacitors are charging up by the same amount, then the voltage here, where they join, will be half of the voltage at the point here where the step arrives. So the initial value that you would observe in the lab would be a half. The initial current would never be infinite, because in real life wires don't have a zero resistance, and there would be no such thing as a voltage source which didn't have some finite value of Thevenin equivalent resistance in its output. So the current wouldn't be infinite. It would be very large when you first switched on the circuit, but not infinite. So the maths wouldn't actually blow up like the transient simulator thinks it will. But when those very large currents are initially flowing, the resistor is taking no part in the circuit, really. All of the current is flowing into this plate of the capacitor, off this plate, down onto this plate of this capacitor, and off this plate and down to ground. So for those first few moments of the transient response, all of the current is flowing into and out from the capacitors. A similar issue will happen with circuits with inductors in them as well. If I had a circuit here in which the step was put in with an inductor and another inductor down to ground, and there might be a resistor here, for example, then the final value of the current flowing down through this circuit, when everything has stabilized, would be infinite. Because at the end of the step response, when no voltage and no current is changing, the inductors would have a zero impedance. And the transient simulator is not going to be happy with that circuit either. But if you analyze it in a similar way, we can work out its frequency response, j omega L over j omega L plus j omega L R over j omega L plus R, multiply up by j omega L plus R, j omega L times j omega L plus R, all over j omega L times j omega L plus R plus j omega L R. J omega L cancels out from top and bottom, just leaves us with j omega L plus R over j omega L plus 2R. And we can work out our initial value. The initial value of the output is going to be the frequency response when omega is infinite. Well, that's just going to be equal to 1, because these terms, these R terms, are going to be negligible compared to these terms when omega is infinite. And our final value, which is the frequency response when the frequency is 0, is just going to be R over 2R. That's just going to be a half. So the initial and final value theorems are quite happy to tell you what the final value of the output is going to be, even though the mathematics of a transient simulator is going to blow up because the current would be infinite, in theory. Again, in practice, it would never get infinite. Wires would have some finite resistance, and that would limit the current. Moral of the story, this technique of using the initial value, the final value, and the time constant will often work, even when a more formal time domain analysis of the circuit fails. Okay, that's the end of the quick introduction to step responses. You may have noticed that I haven't talked at all about second order step responses yet. That's because second order step responses get really quite interesting, and there's another whole series of videos about those coming up.